Okay, the complex conjugate theorem says you got yourself a polynomial with real coefficients, and you somehow figure out one complex root, a plus bi. Then you're guaranteed you also know another root, a minus bi, the complex conjugate of the first one. So you leave the real part alone and you change the sign of the imaginary part. So, for example, somehow we know we've got some polynomial f of x. We know 2 plus 3i is a root. Who cares how we figured that out? Then we also know that 2 minus 3i will also be a root. So if we know roots, we know factors. Remember, every root corresponds to a factor, and the factors are always x minus the root. So x minus that root is a factor, and x minus that root. Notice I need extra parentheses. These will both be linear factors of our polynomial. So what we will do when we know one complex root, we'll find two at once, we'll multiply these together, and we'll use long division to factor them out at the same time. We never want to do long division or synthetic division with complex numbers, only with real numbers. Of course, real numbers are complex, but you know what I mean. If we have something of the form a plus bi, where b is not 0, we don't want to use synthetic or long division on something like 2 plus 3i. Okay, so here's an example. We're told 2 plus 3i is a root of this guy. So we know 2 plus 3i is a root because we were told that. We know 2 minus 3i. We always keep the first guy the same, change the second one. Don't change both of them. Also a root. How do we know that? By this theorem. That's literally the point here. It's the complex conjugate theorem. So we have two factors, x minus the first one and x minus the second one. Notice I need all these parentheses. What I'm going to do is I'm going to distribute here and turn this into a quadratic that I'm going to factor out of that guy using long division. So first, let's clean up a little bit. There's quite a bit of work to do in these. Let's distribute these negatives. So distributing there, I get a plus. Now I'm going to FOIL-ish. I'm going to take each one of these times each one of those. And you'll see when we multiply these together, because these are complex conjugates, all the i's are going to disappear. They're going to cancel out. We're going to end up with only real numbers in a quadratic factor. So what do we get? X squared minus 2x plus 3ix minus another 2x. I have to take everything on the left times everything on the right. Plus 4 minus 6i minus 3ix plus 6i. And then here, you got to think about this. I'm going to have minus 3i times positive 3i. That will be minus 9i squared. But remember, I squared is negative 1. So this negative 9i squared is really positive 9 because I squared is negative 1. Now, unless you've goofed, all your i's should cancel out. Look, negative 3ix, positive 3ix, minus 6i plus 6i. And of course, I squared is negative 1. So we've got a couple of like terms here. X squared minus 4x And then these guys are like terms. And you could check that. That's what I would recommend at this point. Use quadratic formula on this guy. Set this equal to 0, use quadratic formula. You should get these two roots. That's how you check and make sure you haven't goofed here. Okay, now we're going to factor that out of the original. So I'm going to have, and I can't use synthetic division here. I have to use long division. Into x to the fourth minus 9x cubed 3989 plus 39 minus 89x plus 78. Okay. Oh, the key to long division is make sure you keep your powers lined up. I'm going to scoot this down a little bit so it will all stay on one page, because I'm going to be writing up here. Okay. How many times does x squared go into x to the fourth? X squared. I need to multiply x squared by another x squared. And notice I'm keeping those lined up to get x to the fourth. So multiply through x to the fourth minus 4x cubed. X squared times x is x cubed plus 13x squared. Draw the line, change all your signs, and then just add straight down. These cancel. If they don't cancel, you've done goofed. Minus 5x cubed. What is that? 26x squared. Bring the next guy down. Minus 89. Remember, at the end, if we don't get a remainder of 0, we've done goof somewhere. Okay, now what do I multiply x squared by to get negative 5x cubed? That would be negative 5x. Notice my powers are lining up. So what do we get here? Just multiply through. Don't try to do the multiply and subtract in your head. Multiply through negative 5x cubed plus 20x minus 60. 5 times 13 is 60. Draw the line, change all your signs. These cancel out. If they don't, you've done goofed. I think I get 6x squared minus 29x. I lost my x's there. Those were x's. See, I knew I had to have an x there. I knew something had goofed because my powers better line up. And then plus 78. Okay, what do I multiply x squared by to get 6x squared? 6. So what do we get here? 6x squared. Did I copy wrong? See, I saw right here I was not going to get a remainder of 0. I knew something must have goofed. It's right there. 5 times 13 is not 60. It's 65. I apologize. So I should have had 65 here, which gives me 24. Okay, sorry about that. So 6 times negative 4 is negative 24x. 6 times 13, I guarantee you must be 78. We draw the line, we change all the signs, and we add straight down, and I get a remainder of 0. If I don't get a remainder of 0, I've done goof somewhere. Okay, x squared minus 5x plus 6. That factors again. Remember, our goal was to get down to linear factors. We started with a 4th degree polynomial. I need 4 linear factors. I'm going to have 4 roots. I could use quadratic formula here, but come on, that factors x minus 2, x minus 3. So that means that original polynomial, f of x, could be written as x minus, did we have 2 plus 3i? Yeah. X minus, and then in parentheses, 2 minus 3i, x minus 2, and x minus 3. Fourth degree polynomial, we've got 4 linear factors. Remember, they won't always necessarily be distinct, but these are. And then my roots, also known as zeros, are 2 plus 3i, 2 minus 3i. Complex roots will always come as complex conjugate pairs, 2 and 3. My x-intercepts. X-intercepts never correspond with complex roots. These won't give me x-intercepts. These will. Remember, intercepts are points, not numbers. 0, 2, or 2, sorry, 2, 0, 3, 0. And then we could graph if we wanted to. Like we know the end behavior, leading coefficient, all that stuff. This is a good place to stop, though.